So this is the another video on general relativity, and I guess this is part 5 or 6. So in this particular video we are going to discuss about the derivation of the Christoffel symbol. So yes, I have discussed about this in my previous video, but actually what I had done is that I had only able to provide you about the geometrical interpretations of what the Christoffel symbol is, but what's the actual derivation of the Christoffel symbol, I had preserved it, and I thought that I will present it in the future. And so now it's time to discuss about this particular Christoffel symbol derivation, because you have now a base for calculating the Christoffel symbol, and you now understand Christoffel symbol in a much more better way, that how it defines the dot product between the two basis vectors and how it is related with the metric tensor and all that stuffs. So let's start our video. First of all, I will provide you a simple interpretation of how actually this particular Christoffel symbol is visualized. So let's say we have Christoffel symbol. It's denoted by a gamma. I guess you all know about that. This is a gamma. And suppose that I take here lambda and here mu and nu. So the meaning of this particular symbol, let me clarify it a little bit. Okay, so the meaning of this particular symbol, gamma, and here upper indices you can see here is lambda and here is mu nu. So this is equivalent to saying the partial derivative of our this particular e mu basis vector with respect to the e nu into e of lambda. 1 minute, here lambda is the upper index. Okay, this is the definition of saying the Christoffel symbol, gamma, mu nu and lambda. As you can see that how I have positioned the indices here in this particular gamma, and this is the precise notation of what actually it looks like. So this is generally nothing, it's just the, you can say that the changes of the basis vector in the direction of e lambda when we change our e mu with respect to the e nu. So this is the general geometric interpretation, that how it you can say that it encounters, or you can, it describes the changes of the basis vector in the direction of other basis vector. This is the basic definition of what you can understand the Christoffel symbol, what it is. Like it is like saying that how this particular e mu changes, while differentiating it with respect to the e nu in the direction of e lambda. So this is what the geometrical interpretation means. And I have also discussed about this, that why this is important, because there is no any flat space time, there is curved space time, and at curved space time you have not like a very simple system like you have discussed in the Cartesian coordinate. You have not like ijk3 orthogonal basis vector. Here in the curved space there are no such things which really simplifies all the stuff. Here you have to deal with some of the abstract construct or abstract concept where this I and j are not, or you can say that these basis vectors are not perpendicular. These basis vectors are changing. But in the general Euclidean space, what you have studied in the general physics, this particular I, j, k doesn't changes. So this is the basic meaning of defining the Christoffel symbol, because now you are not dealing with some sort of simple version of the Euclidean space where you have only flat space and you have a very constant, or you can say that orthogonal sets of basis vectors. You have everything different in the curved space time, and that is the main motto of doing differential geometry, and that is the main motto of discussing about this Christoffel symbol, because not always there is a simple path of something. I guess you all know about that what I have discussed now, that why there is a necessity of this particular Christoffel symbol in the general relativity, and why it's very much more important while dealing with the curved spaces where your basis vectors are all also not perpendicular, and also they are not like equal. They changes from one point to another point, and that change is captured by this particular Christoffel symbol. So this is what the basic meaning of the Christoffel symbol is. Now let's move to the derivation part. So the derivation, there is actually a couple of methods of derivation, and the main method generally you see in all the books is using the basic definitions of defining first of all the dot product. Then using a simple relation between the dot product and the Christoffel symbol and doing all that stuff. Okay, and the second method you generally do not find anywhere is the method used while defining the covariant derivative of the metric tensor G. And I hope you know that it is equals to 0. And by equating this, we generally find the Christoffel symbol, because you know that how to define the this is not how to define the covariant derivative of any vector field X. This is very different from what we have encountered in our general physics, that it is not just the partial derivative, also you have the Christoffel symbol because your basis vector is changing, but in the general physics the basis vector is not changing. So I'm not going to discuss about the covariant derivative in this particular video, it's a topic of another video. Here we're going to derive using the first method, which is a general method of first of all defining the metric, then defining dot product and all that stuffs. Okay, so let's start. First of all, let me clear you something. There are some types of notations I'm gonna use. So in the previous slide you can see that I have defined it how to write this particular metric tensor, which is gamma, lambda, mu nu, and of course it is equals to the partial derivative of e mu divided by, with respect to e nu, divided by the partial derivative, you can say, into e of lambda. So okay, so what will happen, I'm going to just multiply this whole equation with e of lambda, but with the lower indices, not the upper indices. And if you're familiar with the tensor notations and how to do the different kinds of manipulations with the indices, you will recognize that if they will multiply with each other, it will become 1. And here on the left hand side you will left it e lambda, Christoffel symbol lambda, mu nu, and it is equals to del mu nu divided by del e nu. So this is the one of the very important formula that we are going to use here in the future. I hope you know that here I'm going to take a note that e lambda into e lambda is equals to 1, because this is generally the property of the canonical delta, that in canonical delta suppose that you have a and b, so if a is equals to b, it is equals to 1. Okay, so this is general indices. You have to do this in the tensor calculus, or else I will also try to teach this. So this is the general definition. This is very important, one of the formula that I'm going to use here to define the formula of it. Now let's move to the part. First of all, let me define an arbitrary dot product and take the derivative of it. What I mean is that, let's say I have defined any two basis vector, let's say mu and nu, okay, and I want to try to differentiate this particular with respect to alpha. So you will say that what this is, I mean, you will, if you first encounter this, that what this del, and here you have written alpha, what is the meaning of this? So the meaning of this, anywhere if you have seen, the meaning of this is del by del of x of alpha. Okay, so this is the general meaning of this, that how this is just a short notation. Okay, just a short notation to define this, that what I have used here. Okay, these are basics. Okay, if you have not done this, no problem, you can take a particular general book in the tensor calculus and you will see the notations on the front of the summary of all the chapters. You will see these notations are pretty popular and used everywhere, because you know you are not going to write all the time this particular lengthy stuff. Okay, now let's move to our topic. We define this here. So how we are going to expand this particular term? So of course this is equals to, using the product rule, e of mu del of alpha e of nu, and plus here e of nu del of alpha e of mu. First of all it will act on this particular e nu, and then it will act on e mu. Okay, so remember here this is nu and this is mu. Okay, nu and mu. I hope you are able to recognize this. So this is the general expand of this particular using the product rule. Now let me make some important equation. What I'm going to do is that I'm going to write out that e of mu del of alpha e nu, this particular term, is equals to, I'm going to transfer this here in this particular left hand side, and it will become del alpha e of mu dot e of nu, okay, and minus e of nu del alpha e of mu. So I have not done anything very fancy. I have just manipulated it and taken this particular term into the left hand side, and you are left with this particular term. So let me call this as equation number 1, because here now I am going to change the indices and doing a lot of manipulations. So you might be confused about this, that how I have done it. That's why I am labeling this particular equation as 1. After before proceeding, what I'm going to do is that I'm going to define the general formula that I have derived how to write this particular Christoffel symbol. So I'm going to substitute this here. This is exactly what it is written here. So I'm going to do this here, but the only difference is that here you have alpha, mu. So I'm going to write it as e of, 1 minute, e of mu, then Christoffel symbol. Okay, here it is lambda, and here it is alpha, mu, and here of course it is e of lambda. I have defined this particular formula, and it is of course equals to this again particular term, which I'm going to write as del of alpha of e of mu dot e of nu, and minus e of nu dot del alpha e of mu. So this is the particular term defining it. If you're confused, you don't have to confuse. Okay, I have just replaced this particular thing with this, and you will ask why. Then you should really have to pause the video and go backward and watch this, that how I have defined this. This is essentially del of mu e nu. This is short form, and using some of the manipulations, that here alpha is mu, so I have put it here alpha, nu, all the things is similar, and here lambda. Okay, so this is our again very important equation. So what I'm gonna do is that I'm gonna erase this as 1, because yes, these two are similar, but I want to emphasize on this particular equation more than the other. Okay, so this is, let's say, our equation number 1, very important. Now what I'm gonna do is that I'm gonna do for mu also, then I'm gonna proceed it for the nu, then I'm gonna proceed it for anything else. So let's define it for our indices nu. I'm generally doing the permutations and the combinations by changing the indices, all that stuffs, to get all of the permutation that I can get from here. So here first of all I have done for the mu, then I'm gonna do change indices, and we have to do this so for alpha, then do it for something else. Okay, so let's start defining it. Now what I'm gonna do is that I'm gonna define the same thing, but now here with the alpha, that alpha is our term which is now not in the partial derivative. Then this lambda will be same, and be careful while putting that what should be the lower indices here, as generally now I am going to proceed with the fact that now my here the differentiation factor with respect to not alpha, now we are going to do it with respect to the mu, and then with respect to the nu. So if I will do with respect to the mu, then of course here should be mu nu, and here it should be of course e lambda, and it is equals to the del of mu e of alpha dot e of nu minus e of, okay, so here it is quite tricky, and not tricky, because here we have e of mu partial derivative, sorry, I have written here gamma, it should be partial derivative, here it should be mu, here should be e of alpha. Let me see that if this is correct. Yes, here I've defined alpha, then here of course it should be e mu. Okay, so this is the correct expression, and this is, let's say, our second equation, and this is also very important. These are our base equations that we are going to use it, we are going to manipulate with it, and yeah, let's see what will happen. So this is our equation, quite long, but let's see what I can do further. So I have defined the partial derivative with respect to first alpha, with respect to mu. Now I am going to define the partial derivative with respect to the nu. So if I will define the partial derivative with respect to the nu, just imagine changing here indices from mu to nu. If you change it from mu to nu, you will get again two sets of equations that will not look like a very lengthy. But again, what I'm going to write here is that if I just substituted it with respect to the nu, then here it should be also E of alpha lambda, but here now it should be nu mu dot e to the power lambda, and it is equals to the del of nu, because now I'm differentiating with the del of mu, and E alpha into the E of mu, and minus, if I have defined that here, should also E of mu and del of nu E of alpha. And this is again our third equation, which is very, very important. Okay, so before proceeding, here is something which I'm gonna replace it. So if you have carefully watched what I have done with the definition of the Christoffel symbol and replacing the partial derivative with respect to the Christoffel symbol, then you will also be able to recognize that here I can also do the same, here I can also do the same, and here I can also do the same. What do you mean by same? So I'm gonna write it here that the last term here, as you can see, that del of alpha E of mu can be also replaced with the Christoffel symbol as this gamma upper indices lambda alpha mu into E of lambda. So I can replace this particular thing. I'm not going to replace it because it will make equation look a lot bigger. I will replace it when I will proceed it in the final position, where I will able to just reconcile all that stuff and try to put it on. So this is, let me try to write it in a small, okay, space is not that much. So what I mean is that del of alpha and E of mu can be written in the form of Christoffel symbol as alpha mu lambda and dot E of lambda. Let's see here, this is this expression I'm writing here. So if you should not confused after all about this lambda should be in the downward position. Okay, now same goes for this particular this term. I can also replace del of mu of E of alpha as the Christoffel symbol lambda mu alpha dot E of lambda. And again, this last particular term I can also replace it. This I can also replace it as del of nu E of alpha is equals to the partial derivative lambda nu alpha dot E, and here lower indices lambda. So here, as you can see, that I have just expanded the expression. The last term here, as you can see, that I can also write it in the form of the Christoffel symbol as I have written here, but I'm not going to substitute it now. You can take it as a note that how the last term also here can also be written in the Christoffel symbol stuff, and I will proceed it and I will try to write it in the last. Okay, now we have three equations. Now all the game is all the manipulations. How, with the help of the manipulations, you can choose any stuff plus, minus, and minus with these three equations, and what can guarantee you the Christoffel symbol. Okay, so let's see. So here I have three equations, 1, 2, and 3. What I'm gonna do is that I'm gonna 1 plus 1 plus 2 plus not plus minus, it's a game of the manipulation, minus 3. I'm gonna plus these two equations, then gonna minus with this particular stuff. So this is this will be quite very much lengthy, you can say, but let me see if I can do this. I can just write out the final result, but this will be, but I want to proceed it even if it's very much lengthy. Okay, so if you will add this 2 and subtract with this, so first of all let me add this particular 2 and see what will happen, and with subtracting with this particular stuff. Okay, so let's proceed it finally. Okay, equation will be quite longer, but no doubt I can give you a hint about solving this. Okay, sorry, I will proceed it. Okay, I will proceed it, no doubt. Okay, so what is our first equation? This is our first equation, this is second equation. First of all, let's plus this, then we will try to. So first step is I'm gonna plus first equation plus second equation, and let's see what will happen. So this is our first equation. If I can copy this equation, okay, leave it, sorry, okay. E of mu of Christoffel symbol lambda, and here it is alpha v dot E of lambda plus, here you have E of lambda Christoffel symbol lambda mu nu dot E of alpha. So adding this, and on the right hand side, yes, we have this two equations which I can write it. These two will as follows, we are going to write it as it is in, and if we will just try to add this up, minus mu, okay. So this will be quite lengthy, so what I'm gonna try to do is that I'm gonna hint you to solve this particular equation. It is quite easy, okay. What I'm gonna write is that if you solve it, means if you'll plus it and minus it, I'm just gonna write that what will be the final result, because if I'm gonna write it all of these equations, then I don't think so that I will proceed it, because it's quite very lengthy. Okay, so you have to just add this and subtract this. I'm gonna write out the last expression that you got while doing this particular operation. So the thing that you got after doing all of that stuff is this. Okay, remember this equation, this is not the final, okay, this is not the final, it is just after solving this equation. 2 of E of mu dot E of lambda and Christoffel symbol lambda alpha nu, and this particular stuff is equals to the del alpha of E of mu dot product E of nu del of nu E of alpha dot product E of nu not mu, because okay, and finally minus del of what, okay, mu, del of mu E of alpha dot E of nu. So this is the whole final equation you will get after you will proceed it. This very important equation, this is the final expression you will get after adding and subtracting all that stuff. I will try to proceed it after that. What you can do, first of all, you can divide this whole expression by 2. So dividing this whole equation by 2, this 2 and 2 will cut out, and if you will divide it 2, and one again thing, by dividing with 2, I want you to multiply this whole equation with the dot product of E of mu and E of rho. Remember, it should be in the upper indices form, and multiply this whole equation. So what it will look like, so it will look like here it as E of mu dot E of rho, okay, E of either it's just lower indices mu, E of lambda, here gamma lambda alpha mu, and it is equals to 1 by half of E of mu dot E of rho, and in bracket you have these stuffs, which is del of alpha dot E of mu dot E of mu. Okay, so you just have to write this here, just write this here. This will be quite long, that's why I'm not writing here. So if you will, you have to just write it, this particular whole equation here. And after doing this, I'm gonna try to point out something very important which is very helpful. First of all, this thing, see this term, okay, you will know what this is. If you have studied the differential geometry, you know that how to represent a metric tensor, let's say G mu nu. So it is nothing, it's just the dot product of E of mu and E of nu, and its inverse is defined as G of mu nu is equals to E of mu dot E of nu. So this is just the inverse metric of the metric tensor. You can inverse of the metric tensor, you can say that this is, And if you multiply this, if you know how to deal with this, this and this will become 1, this and this will become 1, because they are the upper and the lower indices. When you try to multiply it, it will become chronicle delta and then 1. And here you are left with the chronicle delta rho lambda, and here this alpha v, and it is equals to 1 by half of this g mu and rho, which is the inverse metric, and again this particular term. This is quite lengthy, that's why I'm not writing here. So let's depict that whole equation, and you just have to write what here. Okay, this equation you have to write here. This is the final form you get, and after you know that this lambda and lambda will replace it, and you are left with the you have left with gamma, upper indices rho, alpha, mu is equals to 1 by half of g of mu rho, and now I'm going to write it in the final form as del of alpha e of mu dot e of mu nu, and here it is like a plus del of nu e of alpha dot e of nu, and minus del of mu e of nu dot e of alpha, and finally a bracket here. So we have derived the formula using the basic notations and all of that stuff, using basic notation of the index notation and the dot product, all that stuff. So this is our final equation. See it, this is our final equation we are left with. It was quite lengthy how to define it, how to do the manipulation, but we have done it. First of all, we have defined the Christoffel symbol, then we have tried to do the manipulations, deriving it, then adding it, and then how to define some of the basic property using the chronicle delta and inverse metric. You are left with a very magnificent formula in the general relativity, and it is personally one of my favorite formula. Remember, this particular type of Christoffel symbol is also named as the second kind Christoffel symbol. Second kind, okay? There is first kind, which is nothing, is just represented as, you can write rho alpha v, okay? You can say all of these indices in the upper, but here you can say that here one of the indices in the upper end, sorry, all of the indices here is in the lower, but in the second kind, in the second kind you can say one of the indices in the upper indices, and they are related with each other using the metric tensor, as metric tensor is used to lower and upper the indices. Okay, so this was a video on the metric, on the derivation of the Christoffel symbol. Maybe in the next video I will try to cover more as aspect like what is the Lie algebra, how to try to use it in the framework of the mathematics of the general relativity, and also we are going to discuss about covariant derivative. A lot of topics are there in my list, and it's a lot of topic, you know, from, you can say, from particle physics to astrophysics. In astrophysics, I'm also trying to make the video on the Lane-Embrun equation, as there are no any single video on it discussing about how to use the Lane-Embrun equation, as it's very important in the formulations of the radius and the how the radius and the density of the stars are related by it. So apart from this general relativity, astrophysics, apart from this general relativity, one more thing is the astrophysics, first thing, and second, my priority, of course, quantum field theory. As you have to know that how to quantize the quantum field theory, and what exactly the meaning of the quantization in the context of the quantum field theory, and how quantization is very fundamental. As I have discussed about, I guess, 1 to 2 video on this particular quantum field theory, but not in a very rigorous way, but in a very beginner friendly way. But I'm going to start in a very rigorous way, using all of the mathematical aspects, also using yes, Lagrangian and Hamiltonian. Okay, this is very important, Lagrangian and Hamiltonian. These topics are also very important, and I'm going to discuss about it, not in very basic, because there is no requirement, there is no any basics of Lagrangian. There are always the advanced stuffs of Lagrangian and Hamiltonian in the quantum field theory. So this was my video on the derivation of the Christoffel symbol, and also I have referenced some of the topics that I'm going to discuss in the future. So this is the today's video. Thank you for watching.